Okay, so I want to kind of give a little bit of context about today's class and then work a couple examples about finding limits with trig functions. And so one of the things that I want to talk about is kind of what information you know and then what counts in my mind as evidence at this point in the course. So when we first did limits, we did kind of an intuitive approach, and we used graphs or t-tables to find limits. And these really are intuitive approaches to limits. There's more that needs to be proven, and it's not very rigorous to find limits like this, but at this level we're going to say that graphs or t-tables count as evidence about what the limit is. If you know what the graph looks like, or if you can have a function where you can plug in values. And then after that, pretty quickly after that, we proved or kind of showed using these that the limit, let's say as x goes to c of some constant function k was just k. And we showed also that the limit as x goes to c of the identity function was just c. And so we used these two building blocks along with the limit laws that you see in this box to build the limits for polynomial and rational functions. So this is where I asked you to provide properties of limits or to break down these limits into each of the pieces. And so at this point, if you know two limits, so if you know the limit here or here, from either kind of graphically or from one of these two that we developed or from a t-table, then you can use any of the sum, difference, constant rules, product rule, quotient rule, power rule, to find them. And so on the exam, typically the way that these are asked is that you are given a kind of a constrained about what you can use to prove the limit. So it's like, if you know, let's say that the limit as x goes to c of x is c, like if you know this piece of information and this piece of information and the limit properties, then show that this limit exists and tell me what you're doing, right? So I kind of try to make sure that you can demonstrate knowledge of these properties, which are the building blocks for a lot of different things. So this intuition or this desire that we have to kind of just plug in a value relies on continuity of functions, and we really haven't talked at all about continuity. We haven't defined what continuity is, and you need to be able to find the limit without relying on continuity, because the definition of continuity relies on the limit. So if you're using continuity to find the limit, you're creating a circular argument. Okay, so today when I ask you to provide evidence, I think one of these things will suffice for this class. And then we also talked then, I think this was last on Tuesday, about limits of polynomials and limits of rational functions. From those two limits, the limit of a constant function or the limit of the identity function, and these limit rules, we can get these two theorems: what the limit of a polynomial is that I can just plug in, and what the limit of a rational function is that I can just plug in. And now you are welcome to use those. Okay. Then today, please note, none of these really have said anything about the building blocks of trig functions. So today we did a few limits of trig functions, and one of them that we found was that the limit as x goes to 0 of sine theta is equal to 0. And we did that, we used the squeeze theorem. With the inequality, negative absolute value of theta is less than or equal to sine theta is less than or equal to the absolute value of theta. Okay? Okay. And I asked you during class to either provide graphical or t-table evidence, because none of the limit properties apply here to the absolute value function. Now, it's possible to write the absolute value function as a piecewise polynomial, and in that case, then you could apply the limit rules. But we didn't do that, and I think a lot of you, when I mentioned that, thought that that was a little bit, I just want to make sure that you understand the absolute value of theta is just equal to theta when theta is greater than or equal to 0, and it's equal to negative theta when theta is less than or equal to, or I can just put less than. It should be the same value. So I just have to, it's how I take the absolute value, right? When the number's negative, I take the opposite of it. When it's positive, it just stays the same. This is the piecewise function. So you could use this piecewise function and then the limit properties, and the idea that it was a piecewise polynomial to find this limit. Okay, so you could take the limit from the right, the limit from the left, and find this two-sided limit. Okay, so the other property that we talked about was that the limit as x goes to, I keep writing x. Look right here. That's not an x. That should be theta, because that's the variable that we're using. So I'm going to use this. Theta goes to 0 of cosine theta. We didn't do this one, right? We didn't really do cosine theta. What do we do? 1 minus cosine theta. And we said that this was 0 using the squeeze theorem, right? So we use the squeeze theorem that 0 was less than or equal to 1 minus cosine theta is less than or equal to the absolute value of theta. Okay? And we use the squeeze theorem to say that this limit was 0. Now, I just want to make sure that you understand what this means about the limit of cosine. So I'm going to use the sum property to split this first one. The limit as theta goes to 0 of 1 minus, or the difference property, theta goes to 0 of cosine theta is equal to 0. Okay, now I'm going to leave this limit here, the cosine one, because that's the one that I want to know. This limit here, the limit of the constant function, should just be 1. So now I have 1 minus this limit as theta goes to 0 of cosine theta is equal to 0. But what I really want to know is, what is the limit as theta goes to 0 of just cosine theta? Like, I don't really care about this one place. So I can, maybe I'll move the limit over and add the limit to both sides, and then I'll get, you can see that 1 should be this limit as theta goes to 0 of cosine theta. Okay, so now these two things that I know, I want to make sure, now I'm going to use, this is what I know for trig here so far, and then I know the limit as cosine, as theta goes to 0 of cosine. Okay, so I'm going to add this to kind of this list of things that I know, right? So other things that I know on this first page, sine theta, the limit as theta goes to 0 is equal to 0, and then the limit as theta goes to 0 of cosine theta is 1. Okay? And then this final piece that we put in today, that we were going to take as given, that the limit as theta goes to 0 of sine theta over theta is equal to 1. And we can talk, that proof is in your book, and I am happy to write up a video about it, but these are the things that I know on this first page, what I know and what counts as evidence. Okay? Okay. So now we want to find some limits. So we were in section 2.4, and we were talking about these limits that involve this sine theta over theta. So I want to maybe do the first couple that we did in class so that you understand those examples. So I want to say, example 1. So the rest of this should just be examples. So show that the limit as y goes to 0 of cosine y minus 1 over y is equal to 0. Okay, that's what I want to show. Okay, so now I want to, and I said that we want to use the substitution that theta is y over 2. Okay, so we put in y is equal to 2 theta, and we're going to look at this problem. Now, if that's true, so if y is equal to 2 theta, then the limit as y goes to 0 of y over 2 should also be 0, so theta should also be going to 0. So I'm going to change this. This is the change that we made. Theta is going to 0 of cosine of 2 theta minus 1 over 2 theta. And I don't know that this is 0. This is what I want to show. Okay, so I'm going to work with this left-hand side. Okay, and so then I'm going to use this, use the double angle identity. So the limit as theta goes to 0. And I'm going to use the double angle identity this version. 2 theta is equal to 1 minus 2 sine squared theta. Okay? Okay, and then I'm going to plug that in and into the limit. So I have 1 minus 2 sine squared theta minus 1 over 2 theta. Now we used a different one of the three. There are 3 double angle identities for cosine. And so I used a different one in class. Like, don't be confused. It still simplified to this. But since I did it already, I thought I would take the more direct route. And then these ones cancel out, and I get negative 2 sine squared theta over 2 theta. The 2's cancel, and I get the limit as theta goes to 0 of, and I'm going to pull the negative out. Maybe I'll do this in one. I want to make sure that you know I'm using several properties here, and I want to make clear what they are. Okay, so I have this. Okay, now I'm going to use several of the properties. I'm going to use the constant multiplier rule, and I'm also going to use the product rule, or the product. It's called rules or properties. Let me just look. Oh, I have the book. Laws. Oh, your book calls them laws. Okay, constant multiplier law. And then, oh, but kind of, sorry, it is called a rule. And then the product rule. Okay. Inside, it's called these rules. Okay, so I'm going to do that. The constant multiplier says I can just pull out this negative, and the limit as theta goes to 0. And then I want to split sine squared theta up into 2 pieces. Sine theta over theta, because I know what that limit is. And this other piece, limit as theta goes to 0 of just sine theta. Now, if I were to multiply these 2 pieces together, sine theta over theta times sine theta, and I would picture it over 1, I would go back to this piece right here, sine squared theta over theta. Okay? Okay. Now, this limit, the limit as theta goes to 0 sine theta over theta is just 1. The limit as theta goes to 0 of sine theta is 0. We proved that using the squeeze theorem. So this overall limit should be 0. Okay. Now, let's do the other one that we did in class. So I want to find the limit as t goes to 0 of tangent t secant 2t over 3t. Okay? Okay. So I want to try and see if I can uncover this sine theta over theta form in here. right here, I know that this is sine t over cosine t. And since here is a t already in the denominator, I think this will unpack pretty quickly. So I want to say that this is the limit as t goes to 0. Also, if you're really thinking ahead about these things, like this is the piece. I also don't know what the limit of secant as t goes to 0, so I might turn that into a cosine. Okay? So I'm going to do this. Sine t over cosine t times, and secant is 1 over cosine of 2t all over 3t. Now I'm going to multiply together in the numerator. Like all of this is just algebra. I'm just moving it around. So I'm going to multiply these top by top in the numerator over bottom by bottom, still in the numerator. I want to make this comment. You cannot combine these cosine pieces because one has an input value of t and the other has an input variable of 2t, and that means they don't combine. So like, I just want to make this note. So like, if you have cosine t times cosine t, fine. This is cosine squared t because you have two of the exact same things, right? This is cosine t squared. You have two copies of the exact same thing. But that is not what I have here. I have one copy of cosine t and one copy of cosine 2t. And there's not really a way to combine them. Okay. Oh, I forgot. I still have this big denominator, right? Okay. Now this complex fraction, I'm going to say most of the time, especially once you get used to it, you'll just write this as sine t and realize that the 3t moves here. If you want to see why that is, this is sine t. I'm going to go right here, right? Sine t over cosine t cosine 2t divided by 3t. But we know that dividing is the same thing as multiplying by the reciprocal. So, and then I just multiply across the top. So sine t times 1 gives me sine t, and then this 3t gets stuck. It gets multiplied, but there's no way to combine it with either of my other pieces. Okay? Now the piece that I want to look at is right here. See this, I'm looking for sine t over t because I know what that limit is, and that's there. So I don't need to do any more algebraic manipulation. I just need to split this up into a couple pieces, a few different limits. So let's say I'm going to go ahead and find this limit. So the limit, I'm going to use the constant. Again, let me write down these rules that I'm using. Constant multiplier rule. I'm going to use the product rule. Okay. And so then I'm going to get the limit. So I'm going to get 1/3. That's the constant multiplier rule. Limit as t goes to 0, sine t over t. The limit as t goes to 0 of 1 over cosine t. And the limit as t goes to 0 of 1 over cosine 2t. And this piece should be 1/3. This piece should be 1. The limit as I go to cosine of each of these should also be 1. So I should get 1/3 as the finishing limit for this. Okay? Okay. I want to do a couple more just in case you still don't like these. That's fine. You may never actually like them, but that's okay. So let's do 23. Right? So in 23, I have the limit as theta goes to 0 of sine square root of 2 theta all over the square root of 2 theta. And this is implied that's all inside the sign. Okay. And what I really want you to see is that this piece, I mean, like, I'm really thinking, like, I really have some limit as of sine theta over theta. as theta goes to 0. And again, this piece is like I just need this thing and this thing to be the same, right? But I have that here, so, and I might just make that explicitly by setting u is equal to square root of theta. Okay. If that's true, the limit as theta goes to 0 of u is equal to the limit as theta goes to 0 of square root of 2 theta. This is just a polynomial. This should be going to 0. So I'm just going to go ahead and change this variable. U goes to 0 of sine u over u. And then this is just 1, just by applying this rule for sine theta over theta that we know. Okay? Okay. Now, 25. Find the limit as y goes to 0 of sine of 3y all over 4y. Okay. In my wishful thinking, I'm really thinking, gosh, I wish, I have to erase this 3, this was a 3. And then I just do the exact same thing that I did in problem 23. No problem, right? Okay, but it's not a 3, so I have to figure out how to turn it into a 3 in order to apply my limit. But it's pretty close to being a 3, maybe. So maybe what I would say is to get the 4 to turn into a 3, like I don't want to subtract anything in the denominator because that messes up, then it messes up my theta over, sine theta over theta thing. But I want to just multiply, because if I multiply by a number, here's what I'm thinking, right? If I multiply by a number, the constant multiplier thing rule helps out, right? And it's much easier to do that than to try and find the limit as y goes to 0 of sine, let's say 3y. Let's say I had this. I had like a 4y minus y something, and maybe I was going to add in another y because I can't just subtract. That would be weird. But I can't, and maybe I just want to say, like I can't really split this up over two denominators. It's complicated. So I don't think, like, this is, like, not the way to go. So I want to just multiply top and bottom maybe by the same number. Or maybe really what I want is I would like for this to be 3y. Okay, so I'm going to write down, maybe I'll just do some wishful thinking, right? I would like for this to be a 3y, right? Okay, I really have to multiply here by 4/3 in order to get it to be a 3y. Does that make sense? Okay, so now this expression here is the same, equivalent to what I had before. So I want to make sure that you understand this. So I want sine 3y over 3y. Now, but that's not what I have. What I have is limit of sine 3y over 4y. Right? So I'm going to try and, like, I kind of like back engineer this thing where I'm like, well, I want it to be a 3y. I have to really like multiply by 4/3 in order to do this. Okay. Now, I'm going to just make sure that we know this 4/3, again, I'm dividing by 4/3, which is the same thing as multiplying by 3/4. So I'm going to put these pieces where they kind of go. So this really looks like 3 sine 3y over 4 times 3y, right? So this might be another way, is to kind of like think of like multiplying in the top and bottom by the same 3, and then you have this 4 out. That's another, maybe I should have done that. But now I can split this up. Again, constant multiple rule. That's it. I don't really need the product rule here. So I get 3/4. The limit as y goes to 0 of sine 3y over 3y. And really in my head I'm thinking of this trick where I turn u into 3y and take the limit as u goes to 0. But I have done that enough times to kind of say this. And so this is 1. So I should get 3/4. Is that okay? Okay. Let's see. Let's do 27. The limit as x goes to 0 of tan 2x over x. Okay. And so I want to kind of take a look at this and really, like at this point, I don't want you to think there's not a right way to go about this. I'm really trying to work like sine x over x into this problem somehow. So one of the things I can do is turn tan into sine over cosine. Sine 2x over cosine 2x all over x. And again, I'm going to simplify this complex fraction by like dividing by x is the same thing as multiplying by 1 over x. So I'm going to get this sine 2x all over x cosine 2x. Okay. So the piece that I need, and I want to just make sure, I'm going to write in red. So really, I would love this if there were a 2 down here, right? Then I could have the same, piece that I have done all along, and then this sine 2x over 2x, the limit as x goes to 0, would be 1. I can't just randomly add a 2 into the denominator. Now it's not equal to the expression above. But the way I make it equal is to put a 2 right here, right? Oh, and maybe I'm going to put it outside the green box so that I know it's not contained in this limit, right? So I'm going to go ahead and now split this limit up. Again, I'm going to use the constant multiple rule. And the product rule here. Okay, now this red 2 on top pulls out. This sine 2x over 2x, I can do that u trick that I did, or u substitution. It's not really a trick. Cosine 2x, right? Okay, and so this is 2. This limit is 1, and the limit as x goes to 0 of cosine of 2x is also 1. So I get a limit of 2. Okay. Okay, should we do one more? 29. The limit as x goes to 0 of x cosecant 2x all over cosine of 5x. Okay, so I get the limit as x goes to 0. This is x times 1 over sine of 2x over cosine of 5x. Okay, and so now I look ahead. I might take a moment to think about this. And I get x over, then I kind of get sine 2x all over cosine of 5x. And I might put this into one fraction, the limit as x goes to 0, and really I have x over sine 2x cosine 5x. Now, this is super frustrating because I know what the limit of x going to 0 of sine x over x is. That's 1. So I would like to be able to conclude, does that mean, this is my question on the side, that mean that the limit as x goes to 0 of x over sine x is also 1, right? So that's the question. So I would say one of the ways possibly to look at this question is to start with this, because I kind of just want to, I don't want to mess around too much. I want, like, this is the primary question that I want to answer. So I'm just going to try and find limit as x goes to 0 of x over sine x, right? But this is the limit as x goes to 0 of sine x over x to the minus 1 power, right? Okay, so those two expressions are equal to each other. Okay. And so then, like, I'm getting kind of excited. I'm like, well, maybe I can just apply. I want to say, maybe I can just apply this power rule, right? And I look back because it tells me what to do with powers. But then I notice that it has this, and maybe I'll go back up real quick and show you. Look, I get thwarted. This is how I'm trying to solve this problem. Where is this paper? You probably have it in front of you. Right here. Ugh. And then I look right here. This tiny little phrase is like, nope, you can't do it because n has to be a positive integer. Okay, fine, right? I still have this guy here because really all I want is to kind of flip this thing upside down. So I'm going to do that. I'm going to use this quotient rule instead because that will work better. The power rule does not give me what I want. Okay. So I'm coming down here. Let's look. Okay, so I tried this. But now this negative 1, this thing still is the limit as x goes to 0. And I'm going to write this in a weird way as this, going back to this complex fraction, 1 over sine x over x, right? Okay, and now I have this quotient rule. Here that says I can split these limits up as long as the limit of the denominator is not 0, and it's not. So I get this limit as x goes to 0 of 1 over the limit as x goes to 0 of sine x over x. And that is 1 over 1, my friends, which is equal to 1. Okay, beautiful. So I'm going to use that right up here where I have sine 2x, right? So I'm going to use, now I know this piece. So I want to say now I know that the limit as x goes to 0 of x over sine x is also equal to 1. Lovely. And then I want to, and I'm almost there, except I want to make sure that you understand in my problem, I need a 2x in the numerator to get this, right? Because I have a 2x in the sign. So I'm going to add in, just as I did before, 2 here, a 2 here. This thing in my green box that gets all swallowed up is right there, right? And otherwise I have to split this stuff up. So I got 1/2 from that first 2 in the denominator. Limit as x goes to 0 of x, 2x over sine 2x. Limit as x goes to 0 of 1 over cosine 5x, right? So I get 1/2 times 1. The limit of cosine is also 1, so I get 1/2. Okay, so I'm giving you a few homework problems to work and to try in this kind of realm. So let me know if you have questions.